Advanced Math Lesson 36. Part A is about angles that are greater than 360 degrees. Okay, it starts out reminding us that we measure angles from the positive x-axis, so that is always the initial side. And the terminal side is the other ray of the angle. So if we think of an angle being what you get from like the distance between the initial side and the terminal side, okay, a 45-degree angle would be right here. This is the terminal side. It's where it ends up. All right, and this with all the arcs on here is showing. So there's our 45-degree angle. Here is negative 315, negative because we're going clockwise, 315 degrees, and that takes you to the same terminal side. We also could have this ray spinning, going the whole way around a circle and then coming an additional 45 degrees. So 360 plus 45 degrees gives us that 405. And that still leaves the terminal side at the exact same place. And then if you're finding, let's say, trig functions of those, the triangle will be the same because the terminal side is always the same. These angles, when they have the same terminal side, they're called coterminal angles. And that's what this is. And I got this little thing I was going to try to demonstrate with. Okay, so if the line over here between, like if green is our first quadrant, okay, positive angles are going that way. We could spin it 360 degrees plus 45. So it didn't only move 45 degrees, it moved 360 plus 45. The way we try to draw it is with these arcs. Okay, and I'll just put a couple little notes on here. We have the thing about coterminal angles. Angles that differ by multiples of 360. The book says integer multiples, so we'll add that. Any angles that differ by multiples of 360 degrees are coterminal. And again, the significance of that for us would be it would give us the same triangle, so whenever you're finding sine or cosine, you often can still use your special triangles for those. Okay, I think we can go ahead and move on to part B. All right, and part B is just about adding trig functions. And so this will provide some practice and putting some things together you've already been doing, but we'll work in some of these angles that are greater than 360. So let's just take a look at example 1. The cosine of 135 degrees. Okay, it's positive, so we're going to go counterclockwise. 135 is over here. 180 minus 135 would be 45. So this is a 1 root 2, but the x is negative. And so cosine of that's adjacent over hypotenuse. That is negative 1 over root 2. We'll simplify that later. And then we have plus, and then we need to do the tangent of 330 degrees. Okay, 330, we'll just put on the same axes here. 330 would be down here. 360 minus 330 is 30. Okay, so this is a 1, 2, root 3. And y is negative. Tangent of the opposite over adjacent, so negative 1 over root 3. And I can just verify that I've got the signs right by remembering all students take calculus. sine is what's positive here, so cosine should be negative, and calculus, cosine is what's positive here, so tangent should be negative. And now I need to add these. I also first need to rationalize the denominators. So let's go root 2 over root 2 here. Okay, so negative root 2 over 2 minus root 3 over 3. And your book mentions the fact that it's acceptable to have your answer like this, as long as we've gotten the square roots out of the denominators. However, for just that little bit of other practice, we're going to go ahead and write this as one fraction. So we're going to get common denominators for these and then be done. So for this one, we'll need 3 over 3, and this one's 2 over 2. So now we have negative 3 root 2 minus 2 root 3 all over 6. And that is all that there is to be done with that. They both have radicals, but different numbers inside, different radicands, so they are not like terms, and that's all we can do with that one. Okay, moving on to example 2. Alright, so now the cosine of negative 60, that's clockwise 60 degrees, so we're down here. That's 60. Then here's 1, 2, root 3. The root 3 is negative. Okay, and so the cosine of that is adjacent over hypotenuse. That will be 1/2. All students take calculus. It is positive. Plus, and then cosine of 210, that would be over here. 210 minus 180 is 30. 1, 2, root 3. The x and y are negative. Cosine is adjacent over hypotenuse, so negative root 3 over 2. These already have common denominators, so then we just write it as one fraction. 1 minus root 3 all over 2. And we're done with that one already. But we still haven't seen any of those with angles that are larger than 360, so let's see what's on the other side. Okay. Now, we know that this will be coterminal with some smaller angle, right? And what we're going to do is subtract 360 from this to see what angle it's coterminal with. I'm just going to write that right here, minus 360. This part is the same as the cosine of 210 degrees. Okay, and this being a negative angle, I'm going to add to this one, and I notice 765 is greater than 720. 720 is a multiple of 360. So I'm going to add 720 to this instead of just adding 360 multiple times. And so now we're getting sine of negative 45 degrees. And then this is what we'll draw the triangles for. So over here we have 210, still down here. That would be 30. This is 1, 2, root 3. Both of these are negative. Cosine is negative root 3 over 2. And then for a negative 45 degrees, we'll be over here. 1, 1 root 2. This one's negative. We're doing sine, that is opposite over hypotenuse, so minus 1 over root 2. Okay, then we will rationalize this one. We now have negative 3 minus root 2 over 2. Okay, because they already have common denominators, so I can just go ahead and write it as one fraction. And that's it. Okay, the only new thing to this is add or subtract some multiple of 360 so that you get it down to an angle that's between 360 and negative 360, and then just do it like normal. Alrighty, now boat in the river problems. These are problems in which boats travel with and against the current, or sometimes it is an airplane and just the air current traveling, like being pushed by the wind or going against the wind. Alright, so when it's a boat, the rate downstream, that would equal the boat's still water rate, how fast it can go when the water is still, plus the rate of the current, because the current is helping it along. We're adding that rate to the rate of the boat in still water. The rate upstream, that's where it's pushing against the current, so that'll slow it down. It'll be the still water rate minus the rate of the current. So this is one of your basically uniform motion problem, distance, rate, and time, but this is how the rates will be affected, just by the current. So let's take a look at example 4. Okay. Almost cut it off. There we go. One day, Selby found that her plane could fly at 5 times the speed of the wind. She flew 396 miles downwind in a half hour, more than it took her to fly 132 miles upwind. What was the speed of her plane in still air, and what was the speed of the wind? Okay, so her plane could fly at 5 times the speed of the wind. So we're going to do, let's make a column headings here. We're going to have downwind, and upwind. Okay. So we're also going to do, let's do our distance, rate, and time. Okay, so her downwind rate, okay, will be her still air rate plus the speed of the wind. Okay, so her still air rate is 5 times the speed of the wind. So this is going to be 6 times the speed of the wind. I guess I'll put rate wind. And upwind will be that still air rate minus the speed of the wind. So that'll be 5 RW minus RW, so 4 times the rate of the wind. Okay, her distance downwind was 396, and upwind was 132. And let's see, she flew downwind in a half hour more than it took her to fly upwind. So downwind time is downwind time is upwind time half hour more, so plus a half. Okay, okay, we'll give her speed in miles per hour, so I want to keep that half, I don't want to make it 30. Okay, so we have this, what was the speed of the wind? So our ultimate goal is to find out what RW is. Okay, well, we have all these columns filled in, so distance equals rate times time. Let's write an equation for this one. That distance, 396, equals this rate, 6 RW times this time, which is TU plus 1/2. Okay, we can also write one for the upwind column. 132 equals 4 RW times TU. Okay, now let's simplify this one on the left. 396 equals 6 RWTU, I'm just distributing, plus, and then half of this, so 3 RW. Okay, I still have too many variables in here. Well, let's see. RWTU, RWTU. All right, so let's divide both sides of this equation by 4 and get RWTU by itself, and then we're going to substitute. So 132 divided by 4, I think that's 33, but I'm still going to do it on my calculator. 132 divided by 4, yep, 33. Okay, so 33 equals RWTU. So now I can put 33 in place of R sub W T sub U over here. 396 equals 6 times 33 plus 3 R sub W. Okay, so that's going to be 198. 6 times 33. We'll subtract 198 from both sides. And that is giving me 198 equals 3 times the rate of the wind. So we divide by 3. The 98 divided by 3, 66. Rate of the wind is 66 miles per hour. Read this again. Oh wait, what was the speed of her plane in still air and what was the speed of the wind? So this is part of it. Okay, now I still need her still air rate. All right, well that was just 5 times the speed of the wind, so we take 5 times this. 66 times 5 is 330. Okay, so this is rate of the wind. That's, I think, evident by that. But then we'll also put still air rate 330 miles per hour. Always go back and read your question, make sure you've answered everything. That's all there is to those. Just a little bit of a twist on your distance, rate, and time problems. I hope you'll find them fun.